Okay, the next section, this section is on properties of radicals. And note that I'm not talking about just square roots, we're talking about a radical. So we've got two benchmarks here. The first is if the nth root of A and the nth root of B are real numbers. And these look a lot like our exponent rules. So if we have an nth root of A times B, you can split this up and multiply the nth root of A times the nth root of B. Now, what usually is true for multiplication is true for division. So if we have a big radical fraction, then you can split those up and divide the individual nth roots. And this is going to be important for us for solving equations. Some other benchmarks that I need to add are if you have an nth root of something and the root and the exponent are the same, then you can just take out the number. Another one is that exponent doesn't have to be under the radical, it can be outside the radical. It serves the same purpose, like that. Okay, now this is if n is odd. If n is even, you have the same thing going, but then you have to look at the absolute value just to make sure you end up with that even principal root. So a thing that is not true that a lot of people try to make true, nth root of A plus B. Some people try to make that equal, but it's not equal. It's not this. So don't try to make this equal. Only true with multiplication and division, not adding and subtracting. Alright, let's look at some examples. Now, when we're wanting to simplify a radical, such as this square root of 98, we're looking for a perfect square that will divide into 98. But let's look at a smaller number. 2 will go to 98 49 times. Okay, now we have a perfect square. The 49 right here is a perfect square. So, we can take out what is a perfect square. Square root of 49. So let's look at this. We've got square root of 2, square root of 49. Square root of 49 is 7. And square root of 2 is the square root of 2. Now let's look at the square root of 24. And a perfect square that goes into 24 is 4. And so we look at this part. Same as square root of 4, square root of 6 gives us 2, square root of 6. So we break down what we can. Now let's look at the next one. It looks a lot like this one, except it is a cube root. And what you need are 3 matching numbers that will come out. So let's look at our old friend the factor tree. We've got 4 times 6, and 4 is 2 times 2, and 6 is 2 times 3. Now cube root says I need to have 3 matching numbers underneath the radical. And I do. I've got 3 2's. So we're going to pull the 2 out. And make sure you put your 3 in your radical right there. And what's left is the 3, and it just stays underneath the radical. Okay, let's look at this. We've got 5 square root 24, 3 square root 8. Now what I like to do here, and have you do, is to begin by rearranging. You can rearrange when you multiply. And then I'm going to put the 24 and the 8 underneath the same radical, but I'm not going to multiply them. But I am going to multiply the 5 and the 3 and make a 15. What I need for the 24 and the 8 is to have a match of the same 2 numbers that I can take out of the square root. Well, I know that 24 is the same as 3 times 8, so I'm going to rewrite 24 is 3 times 8. And there I have my matched pair of numbers in this 8. So that's what I'm going to take out. But I still got to keep my 15. So I've got 15 times 8 times the square root of 3. And that leaves me 120 times the square root of 3. So once again, I want to pull out these cube roots. And we're going to do the same thing that we did with the square roots that were multiplied, rearranging. But this time we need a match of 3 numbers under the radical. So I'm going to rearrange and do 3 times 2. And then the cube root of 10 times 50. Well, I can rewrite 10 and 50. Make that a 6. 10 is 2 times 5, and 50 is 5 times 10. And then I can continue rewriting and have 2 times 5 times 5. And then this last 10 down there, I'm going to rewrite as 5 times 2. So what I have now is a triple of numbers, 3 of them, because that root tells me I have to have the triple of numbers. And so this gives me 6 times 5 times the cube root of what's left. And what's left are these 2's. Because things have to come out in 3's, not pairs. And my answer is 30 cube root of 4. Now make sure you keep bringing your root in each step of your problem. Now let's pull on some problems that have some variables. The number is easy. We'll deal with that first. This is 9 times 2. It's the square root, so we're going to bring out a 3. And what's left is a 2. Now how to deal with the m's? It's got to come out in pairs. So m squared times m. Now that's one way to handle it. If you look at this, I have triplets of m squared, so I can pull that out and leave the last m. But another way to look at it is to divide your exponent by the root. Square root is 2. 2 goes into 5 2 times. Okay? That's that. And it has a remainder of 1, which is that. So that's a little shortcut for you on this one. Except we are going to be looking for 4's that are going to come out. Well, I've got 4 times 8, and 2 times 2 times 2 times 2 times 2. That's 5 of them, but I only need 4. So I'm going to take these out. So that's going to come out as a single 2. And I need to deal with the m's in a minute. So I'm going to leave my remaining 2 in there. Now the m's have to come out in 4's again. So I've got to take 4 m's, and 4 more m's. That gives me 8 m's. And that leaves me with 2. Okay, well I've got 2 sets of 4. This m to the 4th right there means I can just take out an m here and an m here. So I'm taking out m squared, and with 2 m's left over. Again, you can look at it like the exponent 10 divided by 4 goes in twice, and it has a remainder of 2. So this is your exponent on your variable, and this is the exponent of what's left inside. And that's how you deal with the fourth roots with variables. Alright, now with square roots, you see here I have a radical of a fraction. Now it is not proper to write a fraction with a radical in the denominator. So the first thing I want to do is rewrite this. I want to make it square root of 5 over square root of 3. Now, we've learned that with fractions, if you multiply by 1, you're not changing the fraction's value, but you're changing what it looks like. So what we need to get this 3 out from under the radical is to make it a square. So if I multiply it by itself, top and bottom, I'm multiplying by 1, hasn't changed its value, but the square root of 3 times the square root of 3 is positive 3. And the square root of 5 times the square root of 3 is the square root of 15. And this is what we call rationalizing the denominator. Now this next example, I have the square root of 8 over the square root of 25. So let's split it up and make it square root of 8 over the square root of 25. Well, we don't have to multiply by the square root of 25 because the square root of 25 is a perfect square, because the square root of 25 is 5. 8, that's 4 times 2. 4 is my perfect square. I take that out. And now our number in the bottom is a rational number. It's not irrational. So basically that means no radicals in the denominator. Let's look at this one. I need to fix my radical here. It didn't work well. There we go. Okay, so the goal is to get a perfect square in the denominator, where the only thing holding us back from doing that is that square root of 2. But whenever you multiply a number by a radical by itself, a square root by itself, that takes care of the whole problem. But first what we're going to do is start with reducing the 10 over 5, and we can do that easily. But I need to get rid of the radical in the denominator. So remember, whatever you do on the bottom, you've got to do on the top, because you're multiplying by 1 and not changing its value. So now I've got 2 square root 10 over 2. And what it looks like is that these 2's can cancel, so now all we have left is the square root of 10. Okay, so let's look at rationalizing when we have variables. So I've got 12 over the square root of 5a. And so same idea. In order to take something up from under a radical, you've got to have 2 of them and only have 1. So I'm going to multiply by the square root of 5a on the top and the bottom. We're multiplying by 1. We're not changing the value, we're just changing how it looks. So now we have 12 square root 5a on the top, and these 2 multiply to cancel those radicals. And this number is now rationalized. Okay, let's deal with the cube root. The cube root means you've got to have 3 to take out. Here, I only have 1, 5. I need 3. So, let's think about this. If I've got 1 and I need 3, that means I need to multiply by 2 more of those. So, I need to multiply by 2 more cube roots of 5. Well, I can do that all at one time. So, if I'm multiplying by 2 5's multiplied, that's 25, like that. Make sure you're multiplying by the cube root. Okay? Now what this gives me is 4 cube root 25, and on the bottom, it gives me the cube root of 5 cubed, because this one's 5 squared. And this simplifies to 4 cube root 25 over 5. And this is what we're looking to achieve when we rationalize the denominator.